Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Xupeng Yu, who's visiting us today from Munich, where he works for Siemens as well as the University of Munich. He's finishing up his PhD there. He also has degrees from Peking, where I believe he studied math. Is that right?
Yeah, math.
Math's a good thing. It's good for the Constitution. And he's going to be talking to us today about supervised dimensionality reduction with principal components analysis. Sue's here. That's good. She can. She's keep him honest there. And please help me welcome Xupeng. Thank you.
Thanks, Paul. Good morning, everyone. Guys, I'm very glad to come here to give this talk. It's about the supervised dimensionality reduction with the PCA technique. This is two of my advisors, which the first one is in the University of Munich in Germany. Second one is Volker Test with in Siemens Research Lab in Munich. Okay, let's start from the dimensionality reduction. So we are dealing a lot of different problems with the high dimensional data. It could be, so in text, it could be bag of words features. It could be tens of thousands of words here. And for images, we could use many different kind of features to describe an image, so we get a lot of dimensionality here. For web pages, we have text, linkage, and some structure information here. So we are dealing with high dimensional data here. So the motivations of doing dimensionality reduction is that we want to remove some noisy features. So how to remove downweight some of them, or how to improve the learnability. So basically, we want to learn the model instead of have too high dimensionality. And we want to efficiently learn the model, and we want to do some visualization. So this is normally a pre-processing step for many learning tasks. So let's talk about unsupervised and supervised. So most people working on dimensionality reduction, they are working on unsupervised dimensionality reduction. So we are only given the input data. So the most popular method is PCA, the principal component analysis. We will briefly review this in a moment. But we are more interested on the supervised case, so which we are given not only the input features, but also some output feature. So in terms of classification, some people are working on the feature discriminant analysis, which is called FDA, which try to find the directions which maximize within data distance, within class distance, and minimizing the between. Maximize the between class distance and minimizing the within class distance. Second one is for regression data. Some people are working on partial least squares, which is projection methods for regression. We try to find orthogonal directions to maximize correlation between input and output. And if the output variables are random variables, there's CCA, the canonical correlation analysis, which is try to maximize the correlation between inputs and outputs. So we are looking for more general solution. Can we somehow find a solution which can handle all these kind of cases? And how do we do semi-supervised case? Which means we have some data are labeled, some data are not labeled. How do we do semi-supervised dimensionality reduction? So before we go into the detail, we introduce some notations here. We assume we have a set of n data points. And the input features are m-dimensional, so each data point input is xi, belonging to some feature set x. And each point has an output y, which is basically L-dimensional. So this is a very general setting. So we have this matrix here. It's basically n by m matrix for input and n by L matrix for output. And we aim at derive a mapping psi, which maps from the input space to some latent space V, such that V is k-dimensional. So this is outline of the rest of my talk. I will first briefly introduce the PCA technique. Then we'll go into two different approaches for supervised dimensionality reduction. The first one is called multi-output regularized projection, which we'll call MOP. The second one is the supervised probabilistic PCA approach. Then I will briefly say something about related work and some conclusion. The PCA is a very popular method for dimensionality reduction. The motivation is we want to find the k orthogonal projection directions which have the most data variances. So suppose the data are given in the black circle here, then this is the direction of the first principal component, which basically maximizes the data covariance in this direction. The second one is sort of orthogonal to the first one. So because the data is two-dimensional space, so basically we have only two principal components. This PCA have a lot of applications, such as visualization and how to denoise. So basically some of this minor dimension should be noise. And in the text information retrieval, people using PCA to do latent semantic indexing. So how to recover the latent semantics. In the face recognition, people use PCA to do eigenphase, so which basically some leading principal components are some key features of the images, of the face images. So this is the basic algorithm for PCA. We first calculate the mean of the data point, and we centralize data by subtract the mean from each of data point. Then we compute the sample covariance matrix S, which is basically x transpose x divided by n. If the data is sampled, we get this big sum here. Then we do eigendecomposition for this sample covariance matrix S. And we get orthogonal matrix U, and we get the diagonal matrix lambda. Here we assume we sort the eigenvalues in the decreasing order along the diagonal entries of the lambda. So after we do this, the PCA directions are given in the first k columns of the matrix U. They are orthogonal to each other. So if we want to make a projection for a new test data x star, we just left multiply the UK matrix transpose, and we get the k-dimensional projection. So this is some basic algorithm for PCA. And we also have some other interpretations of PCA. So we can do PCA by simply singular value decomposition of the data matrix X. So the algorithm looks like we still centralize data first, and instead of doing eigendecomposition for the covariance matrix S, we do a SVD for the data matrix X. So basically we got two orthogonal matrices V and U. They are both column orthogonal. We get the diagonal matrix D, which have singular values in the diagonal. So after we do this, the PCA directions are given still in the first columns of U, K. So here we use VK and UK to denote the first K columns of the matrix V and U. And DK is basically the top left sub-matrix. It's also diagonal with leading singular values. And we also get the projections of the training data directly in this matrix. So basically, if you left multiplied by the matrix UK, you get this projection for the training data. This SVD solution has a very nice computational cost. So basically, we don't really need to compute the very big matrix S if the dimensionality of data is very high. So here, the X is basically n by m. So it's very small matrix readily. So the equivalence of SVD and PCA can be viewed in this way. If we plug in this SVD of X into this matrix, we calculate S, we can get this form. So this is basically the same form as eigendecomposition of S.
Wouldn't X usually be much bigger than its covariance matrix? The number of points should be bigger than the number of dimensions usually.
And that depends. Sometimes the number of data points is
Much less than the number of dimensions.
yeah. And sometimes you get a very big matrix S, because in the text data you get tens of thousands of features, right? So yeah, there exists a very efficient algorithm to calculating SVD here. So in this sense, we can think the PCA basically try to find the best rank K approximation to the data matrix X in terms of the Frobenius norm of the matrix. So basically, if you truncate the matrix V and U by the first K leading columns, this is basically the best rank K approximation to the data matrix X. It's a very nice interpretation. So how do we do supervised PCA? So PCA is very nice, but it's unsupervised.
So when you subtract the mean, you've made a sparse matrix, in the case of text at least, the sparse matrix really dense?
Yeah, that's correct. If the mean are sort of non-zero, then you make the sparse matrix sort of dense. Yeah, I think this is just a general approach of PCA. I think in terms of I think for some text data, if you think the sort of the mean is not really matter, so you can ignore this step for some text data. That's also my experience. So sometimes you don't really need to do the centralization for text data. Then you still maintain the sparsity of the matrix. So how do we do supervised PCA? PCA is unsupervised, but we could have some output information instead of only the input feature. This could be the classification labels, which could be 0, 1, or could be multi-class. We could have some regression responses, like some real values of each input data. We could have ranking orders, could be labels rank, or could be some preference data. We could have multiple outputs. This is very interesting because sometimes the output is not just one task. You have a sort of multitask setting. So the output dimension is larger than 1. More complicated, you can have structure output and maybe more complicated outputs. But sometimes outputs information are available. So can PCA be biased by these outputs? Which means you can do a PCA-like algorithm which can take into account both input features and output information. And how to do this? So this comes to the second part of the talk. It's basically a way of doing supervised PCA. Here we introduce another interpretation of PCA, which minimizes the reconstruction error of the input data X. So here X is still the data matrix, and we construct this minimization problem. So we minimize the F norm, the square of F norm of X minus matrix product here, subject to the matrix V is identity matrix. So here we constrain that V matrix is basically n by k, and A is k by m. So this matrix is a rank k matrix. From the latent variable model point of view, the V are the latent variables of the model. And here, they just correspond to the PCA projections of the data matrix X. And the matrix A are basically vector loadings, so map from the latent space to the feature space. So this is a sort of dependency structure of the latent variable model. We have k latent variables, we have m features, we have dependency over here. So this is just to try to minimize the reconstruction error from the latent space to the feature space. You can easily show that this is equivalent to PCA up to a scaling factor. In fact, if you assume A is basically this matrix, so if you do SVD, you get X equals to V D U transpose. So this is basically recover the SVD solution if you think A is this way. This is the idea underlying the probabilistic PCA, which we will review briefly later. So we were going to start from this latent variable view of PCA and try to incorporate the output information here. Okay, so let's go from the unsupervised case to supervised case. So what are the key insights of this latent variable model of PCA? The key insight is all the m dimensions of the output of the input feature are conditionally independent if we already know the latent factors. This is somehow the assumption underlying the latent variable model. So given the latent factors, these dimensions are independent to each other. So in this way, we can think the PCA is basically trying to look for a k latent variables that best explain the data covariance. Because after you make this projection, the dimensions of features are independent to each other. So this is a key insight of unsupervised latent variable model. So if we have the outputs y, which is L-dimensional, and so we believe there should be intercovariance between the inputs and outputs. Otherwise, this problem is not learnable. It's not able to predict the y given x. And if the dimensionality of the output is larger than 1, we believe there's some intra-covariance within the y's. this is basically the assumption of multitask learning. So you have multiple tasks, multiple output. There should be some dependency over these tasks. So the idea here is to go from the unsupervised latent variable model to the supervised one. And the latent factors, the k latent factors, to explain both input features and output features. This is basically the idea. And the idea is, with the same key inside of the latent variable model, after you make this projection, we assume all the features and all the output dimensions are conditionally independent. So these latent variables can explain both the covariance structure of the inputs, covariance structure of the outputs, and the intercovariance between the two. So these are what we are interested in here. This is idea. So these are the unsupervised latent variable model and the supervised latent variable model. So if you look at the optimization problem given for this model, this is latent variable model and interpretation for PCA. So we will just need to change the optimization problem from unsupervised case to supervised case. So here we minimize both two parts of the cost. This is the input part. This is the output part. And here we assume the output is also takes the same form as the input for simplicity here. So we have some weight between these two handled by beta. So here the idea is we use the same latent variable V to reconstruct both input and output. And A and B are sort of the matrix loadings for inputs and outputs. Yep.
Is the Y here, is it ground truth or it just some kind of labeling you do when you're in the learning process?
Just the labeling.
Just labeling. Is that a crack? You assume it is a crack labeling or it's a ground truth or whatever labeling you got?
Yeah, whatever the label you got. This is sort of the data you have. This is observation. In terms of classification, you can think Y just the labels. If Y is a regression, Y just some real values. It could be anything. But here we think Y is basically some real numbers in this case. We can sort of extend this further, but I think up to now we just fix this to be F norm here. So the idea is to use latent factors to sort of reconstruct both inputs and outputs. And so this is sort of the K idea, and we have the one parameter beta, which is between 0 and 1 to control the trade-off between these two. But this is not the final optimization problem, because how do we make predictions for new data? So this works well if you have both inputs and outputs for one data point. So you can reconstruct this problem by this way. But you don't really know any outputs for any new data. So for new data, you only have the inputs X. So this is sometimes referred to as the out-of-sample problem for some projection thing. So the idea is to constrain that the projections to be linear in the mappings of X. So we just need to change a little bit. We constrain that the mappings V should be linear in the data matrix X. And we minimize the problem with respect to A, B, and W instead of the V. So this is the final optimization problem we are trying to solve. Okay. So I think the solution to this problem is sort of simple, and you just try to formulate the Lagrange formalism. You try to minimize the enhanced cost here. And turns out that the factor loadings A and B can be determined by the latent variable matrix V and V. So this is just optimal solution for matrix A and B. So you can just plug in this into the optimization problem. You just need to solve this for W. And the minimum value of this cost is the sum of the n minus k smallest eigenvalue of this K matrix. So K matrix is basically a weighted sum of the grand matrix of X and Y. So the cost of this minimization problem is basically the sum over some eigenvalues. It's very nice. So this is the equivalent optimization problem with respect to W matrix here. So you just replug in A and B here. You get this two for W. So this is just a generalized eigenvalue problem for the weight matrix W. So we get the algorithm here. So but in PCA, we first centralize data. So here we do it for both input and output. We calculate the matrix K in this way, and we solve the generalized eigenvalue problem. And we obtain the largest K eigenvalues. And we get these eigenvectors. So the projection, just the linear projection of using these eigenvectors. So we group this K projection, we get the mapping, which maps from the input space to some latent space. So this is basically the algorithm. This is a very nice framework for supervised dimensionality reduction, especially with multiple outputs. So if you take a beta to be 0, you get PCA, because this is just recover the latent variable model of unsupervised learning case. It's easy to extend this framework, so we can sort of try to use some other cost function here. So basically, this is output, this is latent variables. We just need to define some other kind of loss function. If the y is not, say, not Gaussian distributed, you don't really need to use the f norm here. You can use other things. You can use hinge loss here to replace this, things like that. But then you will lose sort of the nice solution that we can directly solve this with the eigenvalue problem. You can also weight different dimensions differently. So, so if you use f norm here, this is basically the sum over all dimensions. So we use the beta L to weight the different dimensions. We get this problem. So it's a little bit general than the original problem. And we can also derive a nonlinear mapping via the kernel trick, which we briefly say something here. So we try to use the representation representer theorem, and we constrain that the W vector is basically linear in X. So we can do this by introducing a regularization term of W norm, and we get this constraint, and we can rewrite everything in terms of the inner product. We centralize data, we calculate the kernel for X and kernel for Y, calculate the BK kernel by reweighting them. We solve this generalized eigenvalue problem using only K's. And we got alpha for eigenvectors with largest K eigenvalue, and we can recover the projection function in terms of sum over the inner product of the data point to this testing data, weighted by the alpha value. This is standard way of doing a nonlinear extension. This is applicable to any RKHS kernels like RBF kernel. So if we assume the beta is 0, then everything is unsupervised, and this takes kernel PCA as a special case. The kernel PCA is just the kernel trick on the PCA, linear PCA solution. Okay, we show some toy data here. These are 3 different kinds of tasks. The first one is basically binary classification. We got this data, we have the labels, red one is +1, and the blue one is -1. So the green line is a PCA mapping, so it ignores anything about the output. And black one is the MOP projection. So basically we can sort of consider the output information to the mapping, we get the correct mapping. This is sort of more informative mapping in terms of supervised case. This is the regression case. We got the label, so from this side to this side, we get the value from +1 to -1. But it's not just a binary case. It's a real number. You see the color is changing here. So between here is almost 0, and this is 1, this is -1. So this is a regression problem. Again, if you do PCA, you get this direction. If you do MOP, you get this one. And last one here is a multi-label classification, which you cannot do with LDA, with facial discriminant analysis, because we have sort of 3 Gaussians, and we assume that these 2 belongs to the first class. So you get 2 classification problem. The first one, take this 2 as +1, take the blue one as -1. And the second classification problem, take this 2 as +1, and take this one as -1. So we use a square to denote the label for the second classification problem. So if you do PCA, you get this. This is basically the maximal variance direction. But if you do MOP, you get this one. And it's more informative, because if you somehow project data into this space, you can sort of separate the 2 classes somehow, because this one is not very informative because somehow this class is mixed because it belongs to both classification problem. So a direction of this way is more informative to separate the two classes. So that means we can handle both kind of all these kind of outputs in this model. And we also did some visualization on data, which is very interesting. We collect 642 art paintings from 47 artists, and we extract some low-level features, which are just color features, curriculum, and wavelet. We ask 170 people to give some labels, just plus or minus one, for these images. So this is, we can take this as output features. This is input features. And if there's missing entry, we just fill in with the mean preferences of this user. And we do a kernelized version of MOP. We fix this as a kernel width. And we just use beta to fix beta to be 0.5 after we balance the trace of two kernels.
So what's the problem? What are you trying to specify this page then?
For this one?
Yeah.
For that, we just want to visualize. So we want to visualize we are showing this figure. So this is a two-dimensional projection of kernel PCA. We projected this four painters' work into a two-dimensional space in this way. And we show some images here. And we will show another projection which is for MOP. But this one is for kernel PCA, so you can see the painting from different artists is sort of separate a little bit. So this is a green part, this is a black stars, this is a red one, this is a blue one. So somehow it's separated for different different painters.
Sorry, could you explain the labels here again? Yeah. You said it was just preferences.
Yeah, just plus one, minus one.
If I look at a painting, I do or don't like it, and is that what you mean by preference here? What do you mean by preferences?
So basically, we have 170 output dimensions. Each dimension is just one user. This user gives some preference labels to, maybe I should not use preferences label. I just use classification data, okay. Plus one means this user likes this image. And minus one means this user doesn't like this image.
It is like and don't like. It's a subjective label.
Just a descriptive label, yeah. So there's no, there's no pairwise preferences, just a plus one, minus one. So every output is basically a plus one, minus one vector for all the images. And we have 170 vector like this. So this is output, this is input. The thing is to try to look at the difference between the unsupervised mapping and supervised mapping. And in supervised mapping, it's interesting, we can recover the sort of common interest from the users. So this is a visualization of the data for kernel MOP. And we get roughly 3 different clusters here. And
there was a graph for one back. Sorry. So it's kernel PCA.
This is kernel PCA on the first 2 dimension. We project data into 2-dimensional space. And we draw the points here. So this is a kernel PCA solution, and this is a supervised projection solution. So we can see some of Van Gogh's paintings and more nice paintings are sort of mixed together. So this mapping takes into account the labels from the users. So they somehow represent the preferences of this user somehow. So you can learn that these images are very similar in terms of the preferences data. It's not just the pure input features. You consider the preference data. And you can see these 3, V1, V2, and V1, V2, and 3. These 3 are sort of Van Gogh's self-portraits. And you can see here they are very close because one user would very likely to like all of them or dislike all of them. So they are mapped very close. But if you look at the kernel PCA solution, they are mapped to very different place because from low-level feature they are very different somehow. So that means in the output the supervised case, you can somehow recover the distance between these 2 input data based on the output feature. And you can also look at other images, and you can see for Dali's work, we get two images here. These are very different from the rest of them, because these images are very similar to this unknown Asian painter's work. It's just about some village stuff. So one user would very likely to like this two besides all the Asian painter's work. But if you look at in the kernel PCA space, they are very far away. D1, the D2, yeah. So that means by using the supervised PCA idea, you can somehow recover the intrinsic similarity of this data point in terms of output. So this is very useful for visualization task.
Excuse me, do you have the comparison between the K mod and the kernel FDA or kernel LDA? Do you have that?
We have it later. This is just for showing some visualization results.
Sounds like a division between the input and the output. It's kind of artificial. Just take them all together and you do PCA.
Excuse me?
The division between the input and the output. And so when you do it unsupervised, just don't take all the data. So basically what you do is you take all your data, you call some of them inputs, call some of them outputs, and then you do PCA.
Yeah.
Obviously, when you put less data inside, you get the results you get less nice.
Yeah, you can somehow interpret this as joint PCA over input and output space, but because of but we have this constraint here. So basically, you want this mapping to be linear in the only inputs only. So because for test data, you don't have any output. So it's not like original PCA for joint space, right? You don't really have output for new data. So this is what you can do to project for test data, right? So it's sort of, you constrain the mapping to be linear in the input space, not in joint space, right?
Weighting the labels very different. You get to choose beta.
Yeah, this is a minor point here.
Half of the data by constant.
Yeah, you're right. This is just a minor point. You get different weight. Yeah, I mean, you are right. Yeah, so I know your point. Basically, I think this is one key point. I think if you look at, there's a technical report 2 years ago by Trevor Hesty's group. They sort of review this kind of method, but they don't know how to generalize, because it's not easy to generalize to new data. Because in the data, you don't have anything about the output for here. So this is just a very easy way to do generalization. So this is the way you can sort of bias the unsupervised learning by some output, but you can also constrain this is linear in X. Yeah.
Since PCA gives you a joint Gaussian model of your input and output.
Yeah.
Couldn't you use, once you have only the input, the conditional mean of the output given the input under this Gaussian joint Gaussian model?
Conditional mean of.
So, right, you have a joint Gaussian over x and y.
Yes.
And now you observe x. Now you have a probabilistic model. You
Yeah.
can say
Yeah.
So would that? So I guess that's different from this. Would that be?
That's a probabilistic approach. That's basically our next work. I will explain this later. Yeah, it's a probabilistic point of view. Yeah.
I'm sorry, but from your application on like visualization, my understanding is that this method is better for differentiating different pictures or different paintings in terms of it's better, which is better than the kernel PCA, right? But from my understanding, because PCA is kind of method to trying to more focusing on representing data rather than differentiating data. So if you can give some examples about how is it better than the Fisher discriminant method or linear discriminant LDA or FDA or whatever you call it. So that one is more focusing on the separability. So maybe I'm wrong, but I do think that if you compare this method to PCA, that is a bit unfair because they're just like the apples and oranges, like they're focusing on different area. That is what I'm concerned.
That's correct. PCA is trying to represent the data, and I think our method is also a sort of generative model for the data. So somehow it's also trying to represent the data, but just by using some output.
You're not using, if you're just representing the data, you're not using the fact that
But-
if a you can project new data,
But
right?
I think that depends on how do you interpret the output, right? If you think output is just a classification, then you try to separate them. But if the output is not just a classification, it's just a regression. You get some labels, you get some real values. This is another extra information you want to put into representation of the data, right?
Just do PCA and all of them. So if you're not using
Then when
example-
new data comes in that's not labeled, you have to do something different. So then you could use this probabilistic model, or you could use this. But all three, I think, are different, and they'll be compared, I guess, later on. So that might you're going to compare against.
Yeah, we're going to compare them. I think, yeah?
So while giving the motivation for MORP, you talked about the graphical model for PCA. So that is effectively factor analysis. Am I right? So the difference between general factor analysis and probabilistic PCA is that the noise model is
Yeah,
not
my model is
accessible.
isotropic.
In probabilistic PCA, it need not be isotropic. It just need to be axis-aligned noise model. So in your model, is the noise also axis-aligned?
In this model, basically noise is isotropic. It's the same as a PPCA solution assumption.
So mean. Okay, so are you talking about means? Are you going to talk about?
I'm going to talk about this later.
The noise model is not axis-aligned. It is general factor analysis. Something compared to that. A variation of MORP.
I didn't compare with factor analysis, but
A variation of MORP which has noise model, which has a more general noise model, because that is usually more applicable to visual data, for example.
I think this model is still based on the PPCA assumption. So basically, the noise is still isotropic. I think here you can have a very nice EM learning here. So it is very simple in terms of learning the projection. And I didn't really compare with this with factor analysis because you can do that. It's no problem. But here we're just focusing on isotropic noise.
So the KPCA does not have access to the label at all. It's just using the input.
Just only the input features.
So it's not a big surprise that the
Yeah, I
MORP
know.
is
I know.
better.
Yeah.
Yeah, I guess this is where I'm confused. So basically, there are two things here: the use of the label, right, and an alternative way to do dimensionality reduction.
Yes.
And you kind of your approach actually is a better use of the label and and better utilization.
I mean,
you know.
the task is to have a mapping which can use both features. How do you do that? Yeah, this is a problem. This is what we're going to do.
Doing that,
There could be other ways. Yes,
and you will be comparing them.
I will compare them later.
Here the comparison is not.
I guess the comparison.
Yeah, here it's just for visualization. It's not for formal comparison. I think because in this data set, the output is not just sort of a multi-class classification. You cannot really use LDA to do that, right? It's a multi-label thing, so it's really not clear how to do this with LDA. So based on this data, I also did some prediction for user preferences. So we split these users to training and test the users in the 10-fold thing. And we use the 9-fold to do supervised dimensional reduction using IBF kernel and project to a 50-dimensional space. And then we try to predict we try to do a standard prediction for test users. And we use linear SVM on the projected space with this number of training data. And we try to predict the rest of them. So here we show them results. We compare the MORP with kernel PCA and also kernel CCA. Kernel CCA is a kernel version of the correlation analysis model. And original features basically we use the IBF kernel SVM to train on the data point directly. So the worst one is using SVM to train on the all data. So this means if you want to make prediction for test users, if you just use low-level features, this is not going to give very good results. So maybe the features are not very informative for making predictions. If you, I'm sorry, this line is the kernel PCA, it's the original features line. This line is kernel PCA. So for kernel PCA, it's a try to reduce dimensionality to 50, so it loses something. And this one is you use kernel CCA. This is the accuracy against the top n number of returned images. So basically, you want to return this number of images. How many of them are sort of really liked by this user? So accuracy actually reflect the performance of system. So you see MOP is very good for all this top n accuracy thing. And when you try to draw the ROC curve here, and you can see MOP is very good in terms of ROC. And kernel CCA is better than PCA. So kernel CCA gives you better results in terms of AOC score. This is just one extra experiment for this user preferences prediction. And how beta influence this projection. So if we let beta to be 0, this leads to just a kernel PCA solution. This is basically unsupervised. This is unsupervised case. And if you lose beta equals to 1, then you somehow constrain that the cost only focus on the output. But the mapping is still linear in terms of input. But somehow this may lead to overfitting, because if you want to generalize to new users, this gives you very poor results. So this is beta equals to 1 results. And this is 0.05. And if you use a good trade-off, which is 0.5, you get better results. So that means a good trade-off is really necessary for this task. This is ROC curve here. You can see if you use beta to be 0.5, you get best ROC value. Okay, so let's brief summary of the MOP. So this is based on a supervised latent variable model. We try to minimize output regularized loss here. And we have the analytical solution for square loss. And we take the PCA and kernel PCA as special cases here. So the problem here is the scalability. So because we want to form if you look at the problem, we need to solve the eigenvalue problem for m by m matrix. It's very huge if m is very large. And how to handle missing data here. So how to choose beta and how to do semi-supervised. This is not very clear in the MOP setting. So solution is to go to probabilistic models. So then we sort of transfer everything into probability thing. So this is a latent variable model. And this is the latent variable model underlying PCA. Where the V here is basically latent variables for x, and mu x is basically the mean vector. And this is a noise process. We assume it's isotropic Gaussian with this noise level, sigma x squared. So V here is k-dimensional, and x is m-dimensional, so Wx is vector loadings from the latent vectors to features. So this is a standard way of doing PPCA in terms of latent variable model. So we still get this conditional independence. So because of this is isotropic, this is a diagonal matrix covariance. So given latent variable, the input is a Gaussian with the mean like this, and with this covariance. So because this is a diagonal, so all the dimensions of x are independent given the latent variable v. And Tipping and Bishop try to prove that if the sigma x squared if we let this to be 0, then PPCA leads to PCA solution. Of course, up to a rotational and a scaling factor. So basically, V are the mappings of x. So if we integrate V out, we can also get the Gaussian distribution for x. So this is basically PV is Gaussian because we assume this latent variable is sort of isotropic Gaussian with identity matrix as a covariance. So this is also Gaussian, so the x is also assumed Gaussian. So this will also give a interpretation of PCA. So PCA basically assumes data is Gaussian distributed. So the supervised case, we just use this latent variable model, and we somehow just use, we assume the same latent variable V generate both x and y in this sense. So the V are shared, and we have different parameters, means and noise level. And here we assume the level of noise level of y is different. It's the sigma y square, but still isotropic. So we still get the conditional independence because given latent variable v, both x and y are independent, and both dimensions are also independent. So this is what we want. And if we integrate v out, so we basically assume that x, y, and y jointly are Gaussian distributed. So this is the supervised PCA model. So semi-supervised case is a little bit trivial in this case because this is the data. We only observe the capital N1 number of inputs and outputs, and for the rest of data, we don't really know the output. So how do we learn a projection model? You try to using both of them, all the inputs and some outputs. So I think this is a little trivial because it's just like a missing data problem in terms of PPCA's model. We just don't know this part of data. That's fine. That's just missing data. So this is a basic idea of the semi-supervised we call PPCA. So here the likelihood of the model, this is all the inputs, this is some outputs. It's basically the product of two parts. The first part is the joint likelihood of the xn and yn for the labeled data. And the second part is just the likelihood of the unlabeled data. Okay, so this part you can see is a sort of PPCA likelihood. This is a supervised PPCA likelihood. So this is just the product of the both. So you can do a very elegant EM learning to optimize the model. So these are the model parameters, the factor loadings, means, and the noise levels. And for the E-step, for the EM learning, we basically use the projection V to be missing data. So in the E-step, we try to estimate this latent variable from the data point. This is basically a projection problem. For a data point which is labeled, so we know both xn and yn. For projection, we try to use Bayes' rule, and we just try to calculate this is the likelihood part, this is the prior part, and this gives you a Gaussian distribution for the latent variable given the observation. And for the unlabeled data, we can also do this, and we only have the input here. So this by Bayes' rule, we just get a little bit different form here, but this is still Gaussian. So this also gives you, if you have a new data, x maybe star, how do you make projections for this new data? You just calculate this posterior. That's it. And for the M step, you try to fix this distribution. You try to maximize likelihood with respect to the parameters. This looks a bit messy, so I don't really put details here. But you can do this very easily. This is it's just the extension of the EM learning for the PPCA model. And this also can be kernelized. This is interesting. This is the EM learning algorithm, but you can write everything in terms of the inner product. So a byproduct of this is basically, if you assume that there's no output, or everything is just input, then we get a EM learning algorithm for kernel PCA. This is a byproduct of this framework.
How would that be useful? KPCA, is it really faster?
Reasonably faster. It's a sort of iterative process, and you can sort of early stopping. You don't really want to get the perfect results. You can do an online version of this. I've shown this in my thesis, and you sort of you can use some part of the past information. You can try to incorporate this new data, and you can do a little bit update. So this is also a very nice interpretation of kernel PCA. If you think about a kernel machine, basically it assumes that in terms of kernel PCA, it assumes that there's a Gaussian in the RKHS space, because PCA actually assumes the data is Gaussian distributed, right? So if you do a mapping to some kernel-induced feature space, then if you use the EM learning, you still assume that the data are Gaussian distributed in the kernel space. This is somehow amazing, but it works for kernel PCA. Okay, let's start from some some toy data here. Again, we're giving a two-class problem, and this is PCA direction. This is a supervised PPCA. It's not fully sort of dominated by the output. It somehow constrains both in this case. And so here is interesting. So you still have the data, but you only observe part of them. So here we assume that the down part and the upper part of the two classes are observed. So this gives you the supervised PCA solution. But if you try to incorporate the unlabeled data, you get this one. It's somehow a trade-off of the supervised case and unsupervised case. So I think one assumption underlying semi-supervised projection is that you are not guaranteed to get better projection space. I think this sort of depends on the assumption here. But you still get very interesting directions to go. In terms of kernel space, this is nonlinear projection. So we sample data from 4 Gaussians. And as you can see, we sort of put the +1 here and the -1 here, so this is not linear separable. We do a kernel PCA. So this is the kernel PCA solution. So it somehow recovers the clustering structure of these 4 Gaussians, but it sort of ignores the labels. And if you do a SPPCA, the first direction is accurately give you the label information. So if you use this one to do classification, it will give you very better results. So this is the project to, this is a high value, this is a low value. This gives you a very nice projection direction. And the second one, third one basically are somehow kernel PCA direction, because this is not reflected in the labels. We use the same data, but we just observe a very small part of the data. So here we assume that only the leftmost and rightmost and upmost and downmost, we only see a very small number of data here. 5, basically, for each cluster. If we just do this supervised PCA on labeled data only, we get this direction, so we can still recover the two-class thing. But it will, I think the contour is like a circle. So because there's no unlabeled data here, it's circle, and it's basically just a pure supervised case. This information is lost, unlabeled data.
Randomly, instead of choosing a little circular blob of labeled stuff, because a circular blob of labeled stuff is going to mislead PCA into thinking, kernel PCA or supervised anything, into thinking that you're talking about a Gaussian. If you sample just, randomly from each of the 4.
Yeah, if you sample randomly, then I think that should be much better. Yes, but I think sometimes you get this data, right? You have really no randomly sampled data. You have only some data. So this is to show if you have this data, if you do semi-supervised, you still get very interesting direction. So this is also you do semi-supervised case, and the contour somehow it's not circle, it's ecliptic, and you get the biased by some unlabeled data for the first direction. And the second one, the third one are somehow biased by the input data. So it's basically recover the kernel PCA solution. So this is different from the pure supervised case. So I think this is interesting to show the difference between these several methods. Which we call S2 PCA, this is semi-supervised probabilistic PCA. We get semi-supervised projection. This is training time for the linear case, primal case, and the dual case. It's linear in the number of data point, in the number of sum over the joint dimensions. Space is linear in number of data point. So this is much cheaper than you directly calculate the eigenvalue problem for the big matrix. In the dual case, you have to calculate the kernel, so the time is n squared. So we can get very nice closed form solution for the supervised case. Let's show some detail here. Just we got some theorem here. It's very formal. So I think the basic idea is if you try to find the stationary point of this EM learning, this is only for supervised PCA. So everything is given. There's no missing data. So we actually try to solve the eigenvalue problem for this matrix S. We call this normalized sample covariance matrix. So this is the input part. This is the output part. This is sort of the correlation between these two. And the mapping direction is basically given by solving an eigenvalue problem for this big matrix. This is n plus L by n plus L. It's very big. And we have a rotational factor R, which is arbitrary rotation. This is the projection for new data. And if you look at this in a dual way, it's interesting because you're actually doing this for this kernel matrix. You try to combine the input kernel, which is the kernel for X, and the kernel for Y, which is linear, based on the variance of these two data, of input and output. And you try to solve the eigenvalue problem for this kernel K, and you get to the projection here. So they somehow sort of interpret that in the MOP, you get some combination of these two kernels, but this kernel actually represents the noise level of different inputs and outputs. This also gives you a way of trying how to learn the beta in MOP. Okay, so yeah, so there's some connections to MOP, and actually the weight of the linear output part and input part is basically the fraction of this two noise level. And we can handle missing data here for MOP if we do this. And unfortunately, if we have supervised, semi-supervised case, there's no closed form because the data are missing, so there's no closed form. We did some standard comparison on a lot of benchmark data. The first table is something about multi-class classification. Second one is about multi-label classification. We have some face data, face images. This data, I think they have about 1,000 dimensions. Yeah, somehow large number of data points for this one. And the second type data is gene data, gene expression data. The dimensionality is very high for this kind of data. But data points is very small. The last one is about text. And I think both dimensionality of data and both data number is very large. And for the multi-label classification, we have gene is EN data and also RCV1 data, which is very, so in the multi-label case, every data point can belong to more than one class. So we basically train a projection model for the data, then we train a linear nearest neighbor classifier after we do projection using the project space. So for multi-classification, we use error rate, and for multi-label classification, we use F1 measure and AUC. We got a big table here. I apologize for this. Maybe it's not easy to see. We project data into 5-dimensional space, 10-dimensional space, and 20. And we compare, this is a full. Basically, we don't really do any projection. We use the original data to calculate the nearest neighbor. PCA is unsupervised, LDA is supervised, PRS is also supervised, and this is supervised, and this is semi-supervised. So actually, in the semi-supervised case, we assume that the test data are already known in the training phase.
So I'm sorry, so after, how do you classify it?
Nearest neighbor. We just use nearest neighbor to classify. Okay. So as you can see, for face data, LDA is really good. I think in this data, our methods can, just in one case, we get better performance than LDA. So LDA this is sort of proved by some other researchers. I think LDA is very good for face recognition. For gene data, for the low dimensional based LDA is good. For higher, I think our method is good. And for text data, our method is very good. So I think LDA is not good for text classification, but our methods are sort of better than the other projection methods. It's multi-class classification, yeah.
Compare against other multi-class classifiers like DAG SVMs or trees or something.
I
mean, PCA isn't even attempting.
But we project data into the same space.
Yeah, well, I think LDA, D is helping here. Discriminative, right?
Yeah, it's a discriminative, yeah. Yeah, I think this method have a limitation that you can only project data into a limited number of projections dimensions. Because in LDA, if you have L classes, you can only project to L-1 directions. But here, we don't have this limitation. And we just try to compare different algorithms in terms of you project in the same space, and you try to calculate distance in the same space. So we don't really compare with other classifier. So okay, and for the multi-label classification, we just compare with the full PCA and PRS and our method. And LDA is not applicable here. And somehow for SVD1, the PLS is not applicable because this data is too large. In this case, our method is always best one, no matter we use any kind of measure and things like that. So this is a general observation. So the semi-supervised one is always better than the supervised one. This is one result. RDA is very good for face data, and our method is very good for text data. And our method can scale to a very large data set. Okay, so we can see some extensions for this probabilistic model. So we can put some priors for the factor loading matrix. So we can do map instead of ML estimate. And we can sort of relax the Gaussian noise model for the output. Because somehow for classification, if you use Gaussian noise, it's not very good. But if you do this, then when you train the projection, you have to do more approximations, like using an EP to approximate it to the Gaussian, things like that. So it's a little bit complicated. And the interesting thing is we can also directly predict the outputs, because we don't really do two-step thing. We just do one step. We don't really first project the data, then do classify. We can do the same thing in the same step. Another thing is we can consider the mixture modeling in this space. I think Tipping and Bishop has applied this to a PPCA model. So it's interesting to consider this in the supervised case. So it's somehow like a local PCA model instead of the global one. So the global PCA is somehow not very good for some manifold learning data. So I think local PCA is somehow better than manifold data. This is very easy to apply in the probabilistic setting, but difficult in the optimization setting, the mixture modeling. Yeah, you can also consider the robust PCA version by replacing the Gaussian with some other distribution student T, and you can remove some outliers in this mapping. Okay, this is some related work. This is most likely to be related work to this work. We compare with FDA, CCA, and PLS. There should be more, but here I just cover the three. For FDA, we try to find directions that maximize between class distance and minimize within class distance. But we have limited number of projection dimensions, and we can only deal with outputs of classification task. And for CCA, they try to maximize the correlation between two, but they try to ignore, but they sort of ignore the covariance between within the inputs and outputs. So in the theorem, show that we are actually maximizing both of them. The PLS is somehow sequentially find orthogonal directions to maximize the covariance. This is somehow a penalized PCA, but you can have bad generalization to new output dimension. Okay, let's come to the conclusion, and we have proposed a general framework for supervised dimension reduction. We can solve this problem analytically by MOP and also iteratively by SPPCA. We have some trade-off between these two because the MOP is optimization based. You can use if you use the other loss function, you can use any optimization framework to solve this problem. And the SPPCA is able to handle semi-supervised case, and we have full scalability. And actually, if you do projection, you can also calculate the variance of projection, somehow noise level. Both algorithms can be kernelized, and we have special cases, a supervised case, and we expect more applications. So this is some results of our work. We get some patent for Siemens company, and we get some papers. I think the most one is appear in KDD this year. And these are some other research topics what I was doing in the last 3 years. Web document segmentation and probabilistic document modeling, also ranking stuff, and yeah, this is some of my work. Yeah, that's it. Thank you very much. Yeah.
I'm worried about the following thing. You want to predict your y, your output, so it looks like a discriminative setting. But you do that by saying, okay, here's x, here's y. Find me the most salient aspects of this data. And so if the most salient aspect is that this and this are very correlated, move together, then you're in luck, and you're going to predict well. If what is most salient is stuff happening in the y or x, say x is a very low dimensional thing, and there's very small correlation between x and y, then it's just going to describe x very well, and you'll have no, you'll spend none of these eigenvectors on predicting y and x. So I don't know if you see that in your experiments, whether you have to modify beta artificially to try to increase, say, the weight of y compared to x so that it stops focusing on x only. And
I think the first thing is you have some parameters to tune here. So if you say I want to concentrate on x more than y, then you can sort of have the sense of tuning this parameter here. This is possible. So you can go from unsupervised to supervised. So you have this softer way of doing this. I think the second thing is in our experiments we just do some supervised learning to evaluate this. So I think this is the only way that you can evaluate which method is good, right? Because you have I think the eventual goal is to do supervised learning here. I think in terms of representation of the data, I think it's difficult to say, and it's difficult to evaluate, right? Even if you have some output. So I think the idea is to try to use all the information you have to get a better better projection. So if the goal is to do projection only, I think this is the framework you can try, and it tells you that the low level dimensionality space that can expand both the inputs and the correlation between inputs and outputs. So this somehow gives you more insight of the projection. Yeah, if you think about outputs as a sort of additional dimension of the input, then you can sort of borrow information there to represent the data well.
Okay. Well, thank you very much.
Thank you.